So hopefully you've had a go at guessing where the centroids of these shapes are. What I'm going to do in this, so you just remembering that to find a centroid, what you're doing is you're just looking for the point. If you put this flat, put your finger underneath it, where's the point that it would balance? That's all you're trying to discover. That's just what the centroid means. So a centroid being for a two-dimensional shape, if there was a plate, the position of that centroid would be the same as the position on plan of the center of gravity of that plate. Okay, so centroid belongs to the shape, center of gravity belongs to the 3D object. So you can do it just by, well, you can guess where it is just by thinking about how to make this thing balance, but there's a few tricks. What you do have to do is you have to learn some of these rules for where the centroid sits, but there are some tricks you can use so that you don't have to memorize too much. So let's just have a look at what some of those are. So you imagine the centroid is the balance point, and so if you've got anything that's a line of symmetry, for example, for a rectangle, so you're thinking of a mirror line, that's what a line of symmetry is. What color will I use here? For might be better off just with black so it's nice and clear to see. So that would be a mirror line. You could fold that shape in half and it would match up. You'll have done that at school. And there'd be another mirror line here. And so if you think not very well drawn, you just have to excuse me. I'm not going to be able to draw these super accurately here. It's just to give you an idea. So you've got a couple of mirror lines in that rectangle shape. The centroid must always lie on the mirror line because that mirror line has the same amount of material on both sides. So if you put something under there, a support under there, and hold it flat, then it'll balance at that point. And similarly, the centroid must also lie on this mirror line somewhere. And so if you can find two lines of symmetry, two mirror lines, then the centroid must lie at the intersection of those. This could be interesting. Let me just see if I can get this to work. Might not be able to do this, or I might. Okay, and so that's a little symbol for the centroid or a center of gravity. So it's lying on the mirror lines. Actually, for a rectangle, often you can also do it as well with the diagonals. Now these are not mirror lines, but the shape on both sides is the same. So you can imagine it'll balance along that line somewhere. And so for something like a rectangle, two ways you can do it. You could either find those lines of symmetry, or you could think about it in terms of the diagonals of that shape, and the centroid will lie at the intersection of those. Now, when we're talking about these centroids or centers of gravity, what we'll often do is we'll often express them in terms of x and y. So I'll just show you this now. And so you'll think about having x and y axes. You have an x at y axis going the other way. And then what they might do is specify the coordinates of that centroid or the center of gravity in terms of the x and y axes. And usually the symbol for the position of the centroid is just x with a line on top, x bar they call it. So x bar. And so say for a rectangle, if that distance was b, just have a think about it, and we'll call that, that distance is b, and this distance was a, then the x coordinate of that centroid, the x position of the centroid would just be b upon 2, and the y position of the centroid would just be a upon 2. Now if we think about that parallelogram, it doesn't have lines of symmetry. It does have rotational symmetry, and in fact the centroid will be at that point of rotational symmetry. But what we can do is, for something like a parallelogram, although it doesn't have lines of symmetry, it's got no mirror lines, but what we can do is we can draw the diagonals again, and the centroid will be at where those diagonals cross. So very similar to the rectangle, and you can find it that way. And then if you're given some more information, not very well drawn, but if you're given some more information, you'll be able to find, like if you know these angles, then you could probably use trig to find the x coordinate and the y coordinate of that centroid. So regular pentagon. So it's just showing that you don't really have to remember these for every shape. You can kind of figure out where the centroid is just by thinking about it. Again, this has lines of symmetry. So for example, it's got a line of symmetry through there, a mirror line through there, and the distance on each side here is equal. That's what those little dashes mean. It means you've got equal distance on both sides. I suppose also you could say this is a right angle as well. It's got both of those things, and then you'd have another diagonal. You could choose any of them, choose any of the other diagonals. So that's a right angle. This is the same. In fact, these lengths are the same as the first one that we showed. So we could just do a single tick on those. If these were the same but a different length from the first two, we'd do 2 ticks there. So then again, so we're just going to get the centroid is where those cross. And I could have used any of those lines of symmetry for that shape, and the centroid is going to be at that position. Regular hexagon, just exactly the same. So we're just doing the same thing each time. I'll just go through them all. And then what we'll find is some of the ones we'll get in a bit later where they don't have lines of symmetry. It gets a bit more interesting. This time I might choose that line of symmetry. So it goes corner to corner for a hexagon, the line of symmetry or the mirror line. Where those two cross, that's where your center of gravity is going to be. And that's true for also irregular shapes. So if I just move this across, let's see if I can do this. Suppose I've got some shape like this. I don't know, something like this. Let me just see if I can do this. I should be able to copy that. And I should be able to flip it. Join it back together. So if I had a shape like that, so it's got a line of symmetry this way. It doesn't have a line of symmetry horizontally because it's just wouldn't, if you imagine folding it over, it wouldn't fold over and meet itself, or if you put a mirror, it wouldn't look the same on both sides. However, it does have a line of symmetry this way. So therefore, I don't know exactly where the center of gravity is, but I know, it's going to be somewhere down here. It's a bit heavier at this side, so to balance it, you'd have to be down here. But what I do know is that it must be somewhere on that line of symmetry. It might be there, might be a little bit further down, don't really know. Might be a little bit further up here, don't really know. But what you'll find is some questions will just ask you, maybe it will just ask you for the x-coordinate of that line of symmetry. So you might have some axes here. Maybe for this one, the axes would start at that line of symmetry. Who knows? It could be anywhere. So you've got some axes like that. And it might just say find the x position of the centroid or the x-coordinate of the centroid. In this case, you could do that because you could tell them, will it be x equals 0? It's somewhere on this line here. So all the values where x is 0, but we just don't know what the y value is. We don't know how high it is, but we do know where it is horizontally. Mostly in this course, we're looking at kind of more regular shapes. Ellipse, you can do the same thing again. You know that the centroid must be on any line of symmetry. The centroid must lie on that line of symmetry somewhere. You've got another line of symmetry the other way. So the centroid must be here somewhere. So those lines are both halfway up, just going straight through the origin of that ellipse. Ellipse or an oval, different ways of saying the same thing. Equilateral triangle, again, just exactly the same rule again. You can find the center of the centroid of that shape, or the center of gravity of a plate that's got that shape. You could just draw on two lines of symmetry. Again, this would be a right angle. These two sides would be the same length. This would also be a right angle. These two would be the same length because it's just saying this is halfway along this line. So this length is the same as this length. Again, if you can find two lines of symmetry that cross, you can then find out where your center of gravity is. Now for triangles, there's another rule. So if you look at a side, so suppose you take this side here, then the height is just the perpendicular distance to the opposite corner of the triangle. That's what the height of that is. So you look at perpendicular distance, so it's got a right angle here, and you draw a line from the line from the bottom side, draw a line straight up to the other corner at right angles. That's your height, and that can help you if you've got axes like this. You're trying to find where the centroid is on these axes. So we've got a y-axis this way. We've got an x-axis the other way. And it might say, what's the y-coordinate of the centroid? There is a rule for that you just learn. And the rule is that the y is equal to 1/3 h. And h is just this perpendicular distance to the here. Try and get that flat. So that's your h, the perpendicular distance to the top. It's this distance here, from here down to here. Okay, so y dash would be 1/3 the height. Now, you just got to be a little bit careful about that. We'll maybe get to that in a minute. There's a couple of examples that will help you for your tutorial sheet. There's a few examples where you've got a triangle like so. And if you were trying to find the y position of that centroid, so we might have y like so and x the other way. In this case, that's your side, but the point isn't above the side. So you've got a side here, but the point's not above it, the point's over here. So the height of that triangle is this distance. It actually sits outside the triangle. So the height would be here somewhere. So that would be h. And your centroid would lie in a line somewhere along here, 1/3 of h. So it would be 1/3 of the way up h from that side you started from. So it might be here somewhere. We could find out exactly where it is because we can use, well, I haven't really talked about that yet. There's another rule for finding the centroid of a triangle. Quite a few rules for centroids of triangles. So what we could do is find the halfway point of this line. So that length and that length are the same. And then find the halfway point of one of the other sides. So say here. So this length is the same as this length. I'm doing 2 ticks because this length is the same as that length, but it's not the same as this length. So I'm using 2 ticks there. So then we would draw what's called, I think it's called the median. It's been too long since I've done this, but I think it's called the median. You'll draw a line to there. And then from the other corner down to that halfway point. And the centroid will be where those two cross. I could have used the other median, so this one across here would have got the same answer. So my centroid's in here somewhere. And what you'll find is that this height here is going to be 1/3 of the total height, that position of that centroid. But you've just got to be careful about where that height is for different triangles, and just be careful you're always going perpendicular up from that base, perpendicular. So for a general triangle, so that's what I just talked about, that always works. Is what you do is you find halfway on one side, find halfway on another side, draw a line from the corner to that. It might be at right angles or it might not be. And then do the same for the other one. You could have chosen the side that I haven't used here, doesn't really matter. And just so people know what we're doing, this length is the same as this length, and this length is the same as that length, and the centroid is going to end up being here, where those two lines cross. Now, where would be our 1/3 height rule? Well, what we could do is we'd start from this side. So we'd think about that side and we'd go perpendicular from that to the other corner. So it's perpendicular from that up to here. What is the angle? So that's 31. So I've gone 31. Need to go another 59 to get to 90 degrees. So it's at right angles. And so you could have found another way. So that's height here. And what you'd find is going parallel to this side here. If I just take that out there, the height here, so that there, taking the height perpendicular from this side, it's 59, wasn't it? And then if we went all the way to the top of that thing, perpendicularly, is it 31? Then this here is going to be 1/3 the height of the triangle, and this, whereas this is the height of the triangle. Okay, so that's your height here. So this here is the same as this. That's just the height of your triangle there. The position of that centroid is going to be 1/3 of the height from the base, perpendicular from the base. So you just have to be careful about the orientation of these triangles. So you're thinking about that rule. It's 1/3 of the height, but you have to find where exactly the height is, and then just make sure you're going 1/3 of the way up there. So it's going to be here on this line somewhere. Okay, So that's that. So just for triangles, you've got a couple of rules. The first one is you draw the median. So you draw halfway along one side and then join it with a line from the other corner. Draw halfway along one side. It's not a good one to choose because those are both height and median. This one's better. You're drawing the median. It's got joins a point halfway along this side with the other corner. Then we've chosen another median. We find a point halfway along this side and join it to the other corner. And where those cross, that's where your centroid is going to be, or if it was a plate, the center of gravity. But there's another rule. The other rule is you find a height, and the centroid, the position in this direction, going straight upwards, will be 1/3 of the total height. So that 1/3, just be aware that that's not the same direction as the median. It's perpendicular from the base. Okay, isosceles triangle should be a bit easier because we know that we've got a line of symmetry. So you've got a line of symmetry like so. We don't have a line of symmetry in the other direction, but we can use that median rule. So we could find a point halfway along this side. So this length is equal to that length. You just split that line in half. You could draw that median. Hopefully this works. Just don't have quite enough adjustment in my ruler. It's as close as I'm going to get. So we're going to get a centroid here. And so that's just using the medians. We can also use the 1/3 height rule. So what's the height of this? Well, it's the same thing. This here is a right angle. Oops. So that's a right angle with that side. So this is not only a median for this side, it's also the height of this isosceles triangle. And so the height is this distance. And the position of that centroid in the same direction is going to be 1/3 of that. So that's the height. The position of the centroid in this direction, perpendicular to the base, is going to be 1/3 of that. So if that's, So if this here is h, this here is going to be 1/3 h. Right angle triangle. What we tend to do with right angle triangles is you could use the medians. Let's just do, you could use the medians, so you could just do the same thing as usual. It'll work for any triangle, the medians. But because we've got that right angle, what we usually do is it's a bit more convenient to use the 1/3 of the height, because what you've got is, because it's right angled, from this side, that's the height. It's perpendicular distance from that side. And we've also got from this side, this is the height. And so for right angle triangles, it's often easier just to think about the 1/3 height rule. And so what we would do is, let's just see what this is actually. See if we can, it's going to take too long. But you'd measure that distance. Then you'd find 1/3 of it, so this would be h. You'd find 1/3 of that, which might be about there somewhere. And so the centroid must lie on that line somewhere. So this distance here is 1/3 h. Similarly for the other side, I'm thinking of this side. The height is the perpendicular distance to the other corner. And so you'd have h like so. So that would be your height, because it's, just imagine rotating this around the other way. Put this flat on, if you put this side flat on the ground, you can see why that's the height. And so this would be height. Position of the centroid would be about 1/3 of the length along there. So probably about here. And so your centroid must be along this line somewhere, because it's 1/3 of the height. And so you could just find where those two lines cross. That's going to be your center of gravity. If you were to do medians, it might not exactly agree because it's a bit of a rough drawing. About here, might just about work. Good, just because I'm doing this kind of roughly, it might not exactly line up, but that would be my median here. Well, has worked quite well actually. That would be my median here. These were just estimated as well, these 1/3s. Okay, so you see there's different methods, you get the same result, but for a right angle triangle, it's usually quicker just to think about the 1/3 height rule. Okay, just be careful, you're always going from that right angle. So you go in 1/3 of the distance this way, 1/3 of the distance this way, and find out where they cross. Okay, so you're always starting from that right angle. So it might be in a different orientation, and as if by magic, I've got one here. So this time you'd have 1/3 along this side. So we could call this, doesn't have to be height, you could call this A and B. And so you could say, doesn't really look like a third, does it? So let's just fix that. Just a third would be about here somewhere, probably. So that would be 1/3 of the length of that side, because it's just the height. That side is the height. Then you'd have 1/3, there's a third there somewhere, 1/3 B this way, if B is the length of that side. So then you draw a parallel line here, and your centroid would be here. Okay, lots of different ones for triangles. They can catch you out triangles, so just be careful with them. Now we're getting back to stuff that's a bit easier again. Not so much. We'll find out about that in a minute. Circle's easy. The balance point smack bang in the middle. So you just take it goes to the center, because there's infinite lines of its symmetry in a circle. But you can have center of gravity, centroid of the shape is in the middle. Center of gravity, if it was a plate, would be there. Semicircle. Okay, we've got one line of symmetry. It goes down here. So we know that the centroid must lie on that line of symmetry somewhere. And then you just have to learn. And so what you do is, in this case, this is just the radius. So the radius is that distance there from the center to the outside of the circle. And it's the same this way. This is also r from here to here. Start here, go up to here. And you just remember the rule, and can I remember it? Is it 3r over 4 pi? I think so. 4 pi, it might be 4r over 3 pi. Hold on, let me check. It's 4r over 3 pi. Who's the teacher here? So 4r over 3 pi. So is the distance up. That sounds about right. And so this is going to be radius. Now, if you want to kind of guesstimate this, it's basically 4 over 3 times 3.142. That's what pi is. That's about 9. So it's about 4 over 9. So it's just a little bit less than half. So 4.5 over 9 would be half. And so it's just a little bit less than halfway up that line. So it's somewhere here. So it makes sense, 4r over 3 pi, so you've got 4 over roughly 9, so 4 over 9, yep. And 4.5 over 9 would be a half, and so it's just a bit less than a half. So that distance there is 4r over 3 pi. So all you really have to remember is this, the one I forgot. All you have to remember is 4r over 3 pi. If you come to a quarter circle, well, there is a line of symmetry on this. And so it's got a line of symmetry here. And so the centroid must lie on that somewhere. And actually, it's the same rule. It's 4r over 3 pi in this direction. And it's 4r over 3 pi in this direction as well. And so the centroid is about here somewhere. Okay? Ellipses. So an ellipse is just a squash circle. So instead of having a radius, this is a quarter of an ellipse. So if it was a full ellipse, have we done a full ellipse? We have. It's just so if it's a full ellipse, it's just at the center, obviously, because that's where it would balance. If you put your finger underneath it, lay it flat, put your finger underneath. This quarter ellipse, on the other hand, it's almost the same rule as a circle. Now, this doesn't have a line of symmetry like the quarter circle does, but we could say that this is A and this is B. So the distance along here, instead of r, it's going to be 4b over 3 pi, the same as the side you're on. And the distance in this direction, I'm not doing this very accurately, is going to be 4a over 3 pi. Okay, so if this side is a, it's going to be 4a over 3 pi, 4b over 3 pi, and you can find your center of gravity. So far we've only really had to learn 2 rules. So for a triangle, if it's a right angled triangle, then it's 1/3 of the way along the side, the two sides that come from the right angle. Remember, you're always doing those with respect to the right angle. Or it's 1/3 of each. If you take any of the sides and you find the perpendicular distance to the other corner, that's the height. If you take 1/3 of that in this direction, it will be 1/3 of the way along that line. Somewhere this way. So it's going to be 1/3 of the way along that line. What else have we learned? We can use the medians for triangles as well. So just half one of the sides and draw a line to the other corner. Do that again with a different side, and then you'll find the centroid from that. And for all the other ones, except the parallelogram, for these ones we just used symmetry to find it. So two lines of symmetry, where they cross, that's the centroid. Parallelogram, draw the diagonals, where they cross, that's the centroid. So there's not that much to remember. Half ellipse, so last one. So say we've got a line of symmetry, so it must be on that line somewhere. And if this was A, so we'd say that this distance here is A, say. And you can still use that same rule. So this is still going to be, if that's A, then the centroid somewhere on this line, we can see how far along that line. It's just equal to 4A upon 3 pi is how you could calculate that distance to the centroid along that line. Hopefully that makes sense. If it doesn't, have a look online. There's guys explaining this online, heaps of videos about this, or have a look at Terry Bennett's notes. Or ask me later if you're unsure of any of those. But that's some different ways to find a centroid. So simplest is if you can find lines of symmetry, two lines of symmetry where they cross, that's where the centroid is. For parallelograms, where the diagonals cross. Triangles, you draw the medians. So just for a general triangle, just draw the medians where they cross, that's the centroid. And then maybe you can use trigonometry to figure out numbers where it is. But otherwise, also works for any triangle. If you find a height, the position of the centroid will be 1/3. So the position of the centroid in that direction, perpendicular from the base, will be 1/3 of the total height. And then we got to, the circle's just in the middle for obvious reasons, right angle triangle, the side is the height. So that's why this works. If that side is A, then the position of the centroid is going to be 1/3 A. If this side is B, the position of the centroid is going to be 1/3 B. Circle, two lines of symmetry, or infinite lines of symmetry, but it's just at the center. Then for the circles and ellipses, we just have to remember this 4R over 3 pi, or 4A over 3 pi, or 4B over 3 pi, for those to find the position. Just bearing in mind, we can still use lines of symmetry to help us. Okay, we'll get on with the next one. Stop that.